All right, so in this video, we're going to talk about free fall. And in the last video and homework, we talked about motion that was only in the horizontal plane, in the x-axis, moving left and right. And then we had our kinematic equations, and then we had the 5 variables that we're always looking for in order to describe our motion. Today, we're going to talk about motion only in the vertical. So up, down, along the y-axis. And free fall is specifically defined when your acceleration is only due to gravity. So the Earth's gravitational field causes us to accelerate towards the surface, and if that's the only acceleration from gravity, then we call that free fall. So the Earth. All of us have mass. Mass creates a gravitational field. Now, the gravitational from us as human beings is very, very small. So small that it has no impact on your life. You've probably never commented it on your gravitational field. But when the mass starts to accumulate in large quantities like the Earth, then the gravitational field does start to affect us. After all, the gravitational field from the Earth is what keeps us to the surface. And the gravitational field is circularly symmetric, spherical in 3 dimensions, meaning that the force of gravity is always pointing towards the center of mass. And it's this symmetry of the gravitational field that actually creates the round objects in space. And the smaller objects don't get crunched into a sphere if they don't have enough gravity to do that, but something like the Earth has enough gravity that crunches it into a sphere. And if we look with these orange lines, the gravitational field, the acceleration from it, is always perpendicular to the Earth's surface because the Earth is round. And if we zoom in and can try to imagine getting closer and closer, our experience is that the Earth's gravitational field is always straight down. So from our perspective, standing on the Earth's surface, the Earth's gravitational field is always pulling us straight down into the ground, all in the y direction. And we've measured that to be 9.8 meters per second squared, the acceleration due to gravity. And if we throw down a standard coordinate system, then the acceleration due to gravity is negative, since it's pointing down in the y direction. So we have free fall when the acceleration is solely due to gravity. And with a standard coordinate system, meaning this right here, then the acceleration due to gravity, commonly called g, little g, is then minus 9.8. Now, in the y direction, the vertical, up and down, we still get the same kinematic equations. However, what we're going to do for up and down is instead of using x in these, we will use y. And so these will just change to y to indicate we're now talking about up and down. And something that may make free fall a little easier to deal with is the acceleration in free fall is always minus 9.8, which then means that there's only 4 variables that we have to be looking for instead of 5, which we had in the horizontal left and right. So if you want to check out some problems on that, make sure you see the other video where I work out those problems. So the next topic we have to cover is relative velocity. And this has to do with how you plant your coordinate system. So if you plant it on something that's stationary, or if someone has it on something that's moving, say like a car that's moving or a train. But I'm going to talk about water. Imagine a person just sitting in a boat. They're on the water, and I've tried to draw the ground here to represent Earth. And now it matters where you put your coordinate system. Are you going to put your coordinate system on the boat, which is then going to be affected by how the water flows? Or are you going to put your coordinate system on the Earth, which is just going to stand still? Now, the reality is that the Earth does move around the sun moves around in our galaxy moves around the other galaxies. But from our experience, what seems still to us is the Earth's surface. So very common for Earth to be the reference system that we measure velocities from. And then we consider the Earth as being standing still. It has no velocity. And this is what you measure when you're driving your car or looking at a speedometer. The speedometer is measuring relative to the Earth's surface. The speed you measure in your car is relative to the Earth, and the Earth just standing still. But let's say that we have our engines off in this boat, so just floating there. But the water is actually moving to the right at 5 meters per second. And if I put a little diver here on the bottom, so the diver represents a coordinate system attached to the Earth. The person in a boat represents a coordinate system attached to the moving water. And so the person in a boat, they're going to look at their speedometer, their engines are off, and they're going to say, I'm at rest. I have zero velocity with respect to the water. From their perspective, they're not moving in the water as the water carries them down. But the diver is going to look at this boat and say, actually, you're moving toward me at 5 meters per second with respect to the Earth. And if we put down a standard coordinate system, we can get some sign values in here. So the person in a boat, if they would record the velocity, they're going to record the velocity looking at the diver as being minus 5 meters per second. From the boat's perspective, as their engines are off, floating in the water, from their perspective, it's like the diver is coming towards them. And they would record that velocity then as minus 5 meters per second. While the diver is going to be like, hey, wait, you're actually coming towards me. I record your velocity as plus 5 because you're moving in the positive x direction, moving toward me. And so it seems like maybe that we have some conflict here because we have these two people looking at the same situation but measuring two different values. And this is what we call relative velocity. So it's not that the physics is different for these two people. It's just that the diver is on a coordinate system that's not moving, and the person is in a coordinate system that is moving. And so they are going to measure different results. And again, the boat, whatever the speedometer reads on the boat is with respect to the water. While the diver is going to make all their measurements with respect to the Earth. Another example of relative velocity, so that last one was kind of a side view looking on. Here it would be a bird's eye view, so imagine you're a bird looking down at a river here, and we'll say this river is moving north at 3 meters per second, and so we're measuring that velocity relative to the Earth. And imagine your boat is over here now, and you're going to cross this river. And you're just going to have your boat point straight to the right. That's how you're going to drive your boat. And let's say you drive your boat straight to the right, and this vector, remember a vector has a length and a direction. Let's say that this length is 7 meters per second relative to the water. So that's what we would measure. And you're just going to try to drive straight across. But the water is also pushing you up. And so try to imagine this motion. Your boat is always pointed straight to the right, yet your actual motion is not. And this is something we don't commonly experience when driving our cars. So when you drive your car, your direction of motion comes out of the front of your car. When you're turning, when you're going straight, your direction of motion is always from the front of your car. When this isn't true is when you lose control. So if your car starts to slide, you spin around, your car can move in a direction that is not coming from the front of your car. And when we drive our cars, this is something we don't desire. We want our direction to come out of the front of our car. We've got control, we're stuck to the pavement. But if we lose control, then the direction of our motion may be, say, from the side of our car. But with boats and airplanes, it's pretty common to have motion where your motion is actually not coming out of the front of the boat. So even though your boat, you're looking this way, you're looking straight at the shore, your boat's not actually following that path because your boat engines are making it move to the right, but the water is also pushing you up. And if we throw some numbers down here, so this component here, I'm calling that 7 meters per second relative to the water. Now the water's flowing straight up, so it's not affecting any motion left and right. And when that's true, so our motion is just 7 meters per second to the right. And when that's true, this will also be relative to the earth. So try to imagine the water flowing straight up. There is no part of it that pushes the boat left or right. So this velocity we would measure relative to the water would also be the same velocity we measure relative to the earth. So velocities can be the same depending on how you put down a quarter system, or they could be different. Now, going up, that part of motion is completely from the stream. And so just going back over here to this triangle I'm building, that would have a component going up. And so with our boat pushing us to the right at 7, the water pushing us up with 3, our resultant motion will then be the hypotenuse of this triangle. And now that we have a right triangle, we can use some trigonometry and Pythagorean's theorem. So if we actually wanted to know, well, how fast is the boat actually moving? Because the boat is moving with 7 to the right and 3 up. So how fast is the boat actually moving? Then we would use Pythagorean theorem to get that hypotenuse. And if you need to get this angle right here, you can use, depending on how the information is given to you, so maybe they might give you the hypotenuse and not one of the legs, maybe, depends on how information is given. But if you have just the adjacent and opposite leg, then you can use tangent. And tangent's what's pretty common for getting the angle. And tangent again, remember the SOHCAHTOA? That's what's something really important from trigonometry, so you know how to set up sine, cosine, and tangent functions. And then ultimately on your calculator, you just hit the inverse tangent to get the angle. Make sure also that when you do use your calculator, you're in degrees, since it's very common for physics to do its measurements in degrees versus math, which tends to like radians. And that is relative velocity. Make sure to check out the homework video to see problems worked out. I'll see you in lab.